Hello, good day. We are from Group 8, OCC3 of Applied Machine Learning course. Our topic for today is insights from Uber and Lyft, ride-hailing fare prediction using journey and weather data. My name is Sammy Charlie. Let's move into introduction. Global ride-hailing market has projected to reach around 285 billion by the year of 2030, and they all share a common business model, which is dynamic pricing. And KL peak hours can increase fare prices by at least 40%. This means there is no pricing transparency, and the aim of our project is to build an ML model that predicts e-hail fares based on journey and weather data.
The following section is the literature review. We compared three case studies to identify the best approach for taxi fare prediction. Please look at the comparison matrix on the right. First, the choice error focused on NYC tax data. They used an ensemble learning model and achieved a balanced reason score of 3.26. Second, serial center shift the focus on module. Interestingly, they include weather variables, achieving a range of 3.40 using a random forest model. Third, result error treat this as a classification problem rather than regression prediction price ranges with high accuracy. There is a research gap in using weather data to explain price changes. Our project bridges this gap by combining red record with weather variables. We aim to build a regression model that is more accurate than previous methods.
Let's look into methodology. There are 6 different phases in methodology. First, we integrate data by merging 2 different data sources together and clean the data, explore the data using EDA, pre-process the data and prepare it for modeling, and we will evaluate the results of different models to choose the best result. Now, let's look into data integration and cleaning. From our Kaggle dataset, we have 2 different CSV, cab rides and weather CSV. So for cab rides, it describes the cab journey for Uber and Lyft. There's 10 different columns and around 690,000 rows. Meanwhile, we have weather data that describes the weather condition, around 8 different columns and 6,000 rows. So there is a few now values in prices and rain, but when we join it on the timestamp column, we have a consolidated data frame that looks like this. So in total, we have 18 different columns. Now, after we have done cleaning, we perform our EDA. First, we look into our data distribution. The distribution of cab prices is right skewed, so majority of the cabs are low cost. Meanwhile, for trip distance, majority of the cabs actually do short distance trips rather than long distance. And looking into relationships of our different features, you can see that for price and distance, cab fare actually increase with distance. Like the further your distance is, the more expensive it is. And longer distance actually tend to have a more stable pricing point of view because there is lesser outliers. Whereas when we look into the average price by the hour of day, the higher average prices are early in the morning and during evening. This is quite normal due to peak hours. Now, let's look into the relationship between Uber and Lyft in terms of the price based on the cab type. So we have different cab types based on Lyft and Uber. In general, Lyft luxury services have a higher, medium, and wider spread, which means it has a stronger surge pricing in comparison to Uber. Next, when we look into price efficiency, comparing the price per mile by the trip distance, you can see fare increases with distance, but it's not linear. It's not linearly. But price and distance varies by ride type. You can see here different lines represent different ride type. So based on your cab type, the price will differ. And you can see Uber pool right here dominates the rides most. This blue one, and the share rides are usually cheapest. And we can conclude that Uber is pricier than Lyft.
Before we can perform any modeling, the data needs to be in a format that is interpretable by machine learning algorithms. For the data pre-processing stage, we first construct new features that convey a clearer meaning. For example, temporal features like is peak and is night are constructed from the hour attribute of the timestamp column to tell us whether the ride happened during the night or during peak hours. Weather features that represent cold temperatures and high winds in the form of binary flags are also derived. And a route feature is derived from the concatenation of the source and the destination of the ride. Next, we perform one-hot encoding on the categorical variables into a Boolean representation to make sure that the models don't misinterpret the order between the categories. Numerical data is scaled down to convert the mean of all the features to 0 and the standard deviation to 1 using z-score normalization. This is done to bring down the different magnitudes of all the features down to a common scale. The data is then partitioned into training and testing sets by an 80-20 split to assess the model's learning. For the modeling stage, we used a linear regression model as our baseline as it simply assumes linear relationships between the features. K-nearest neighbors is the second model that we used as it is based on similarity between the points determined by a distance metric. A support vector regression is also used as our third model that relies on finding the maximum margin hyperplane. Random forest is the fourth model that relies on an ensemble of decision trees to learn nonlinear relationships between the features and use bootstrap aggregation to reduce overfitting. XGBoost is our fifth model and is expected to be the best one out of them all, as it improves on the random forest performance by sequentially building the trees and correcting the errors of its predecessor trees. For evaluation, we used mean absolute error to show the magnitude of the errors between the predictions and the true values. Root mean squared errors are reported to show how much the errors were penalized, and R squared value, or the coefficient of determination, is used to report the amount of variance that is captured in the target variable by the model with the given features. According to the table, we can see that XGBoost is the best performing model with the most minimum error of $1.12 between the predicted fare and the actual fare, and is able to capture 96.7% of the variance in the price. The worst model here is KNN, which can be owed to the fact that it suffers from the curse of dimensionality, where as the number of features proliferate in the dataset, the distances between the features become more meaningless, therefore skewing the predictions of the KNN model. Moreover, it can also have performed worse due to the outliers in the price, as we've seen in the exploratory data analysis. To get the maximum performance out of XGBoost, we performed hyperparameter tuning to determine the optimal set of hyperparameters. Randomized search CP was used here to randomly sample parameters and train on 4 folds of training data while evaluating on the holdout set. This was done over 20 iterations. The best parameters were used to train the whole model again and evaluate, giving us the slightly improved results that you can see here.
Hello, Professor. So now we're into the discussion of our results for the XGBoost model that we have run. So we've got the left-hand chart here looking at the actual versus predicted prices. In general, you can see that we're quite close to the line. Maybe the model is predicting slightly under than over, but it's not really obvious or clear. The only thing to maybe point out around the results is that towards the later price points, the model struggles to get as close to the predicted price. But then also you're looking at the fact that the relative percentage difference is going to be larger as well. So that's worth to keep in mind. The results are fairly well distributed. There are a few outliers, but mostly the model is handling the price points. And we don't see that kind of significant fanning out or cone shape where the model is really good at predicting some, but awful for others. It's generally performing quite well. Now we're looking onto the chat plot, and we've also complemented this with the financial impact. Because part of this is, we know from the previous chart, is that we have more values on the lower price point. So we want to see, is there other variables, for example, distance and surge multiplier, they don't have a significant model impact. But for the results which are slightly rarer and have longer distance, and they're using in a peak time, then these results have a really big financial impact. So for example, $2 versus, even though if you looked at Sharp, you'd see 95% and 1%. So this is financial impact is a really good way to contrast between model weight and finance. The other variables to call out is we have the root variable, which we financially engineered. This was successful. It's a Boolean 1-0. Or are you on the most common route? Yes. If so, then we increase the price in most cases, and that clearly worked. Weather and time we tried to feature engineer as well, but it's clear that it didn't really make a significant difference. More so, it's based on demand factors. Thank you.